today as a part of the lecture 13. Phase diagrams are very important. They form the basis for various phase formation, allowing mixing different components to get properties which are much better than the individual components. So, that is why a detailed discussion on the effect of size on these phase diagrams is warranted, and it is important that you know these aspects, so that using the computational tools available nowadays, one can generate this kind of nano phase diagrams for various applications purposes. Even before you do an experiments, you can probe these phase diagrams as a function of size and then understand what might be happening to it. That is very important for you to know. So, now question is how much we can discuss on these aspects, right? That is something which is very important. What I mean to say is that how deep I can discuss about it. So, I am not going to discuss very deep, so that it becomes very tangential to your understanding, because this requires quite a bit of basic fundamentals. So, what did we study in the last lecture? We have discussed about some nano aspects of nano phase diagrams. Okay, this word nano phase diagram means many things. So, that is why it should be quoted as such, as because this is widely used in literature. But what does it mean is the effect of size and curvature on the chemical composition, temperature, and in an effect on the phase diagram itself. As you see, I have shown you this phase diagram again and again. This is copper and nickel phase diagram. Copper and nickel actually is very, the first phase diagram we study in material science or metallurgy, that forms an isomorphous type phase diagram. What is the meaning of isomorphous? Well, if you mix copper and nickel any proportion, whatever proportion it's starting from 0.01% of nickel into copper to 99.9% of nickel into copper, or vice versa. Okay, in this sense, the phase formation is same. That is, you will have a single phase forming. That is the FCC solution between these two elements. So, that means it is from continuous series of solutions, depending on, does not matter what is the composition of the alloy is. So, that is why it is called a isomorphous. That means it looks same. Iso means same, morphous means looking. Okay, morphology is what is the synonymous word of morph. So, it looks same from whatever way you look at it. It is basically length separate phase diagram. All of you know that. Okay, length separate phase diagram in the literature, copper and nickel. Okay, copper has a melting temperature much less than nickel. This is what it looks like. I have drawn it earlier, I am drawing it again. Copper has a melting temperature of 1084 degrees Celsius, and so this is temperature axis 1084 degrees Celsius. Nickel has a melting temperature of 1453 degrees Celsius. Okay, and this is the mole fraction of nickel. So, you add whatever amount of nickel into copper and vice versa, that means copper into nickel or nickel into copper, it forms same phase. So, you can clearly see that phase diagram, which is basically representative of this red color thing here, written as a bulk, is changing, or is depending on the particle size or the diameter or radius of the particle, it is changing. Okay. One thing is very clear, for the pure copper or pure nickel, that is on the both ends here and there, the change is basically melting temperature change because of the size and because of curvature. That we have already discussed. Okay, you can go back to previous lecture where I have discussed about this melting temperature change as a function of size or curvature. Okay, so that is understandable. There is no chemistry involved in that. There is no chemical composition in the pure component of copper or pure nickel. But in between, in the center of the phase diagram, or maybe in the both sides, other than these two pure components, you have an effect of chemical compositions. That is why we need to know how it is going to be affected. Okay. So, while this is in a bigger picture of copper nickel phase diagram, as you see, the bulk one lies there, the red color curves, and the black ones are basically one for radius 10 nanometers, other one is said for radius 5 nanometers. So, what is the meaning of this? These diagrams are calculated using computational tools, like using a program or maybe on a console platform, which even we have in our department, which you can do this. One can write even codes to do that. This is all possible, but the basic fundamental how these things are derived, how you make the calculations, okay, mathematical background of this is required to be known. Then only you can do these things very easily. And you will be doing in your understanding of research, okay, where you are doing nanomaterial research on various alloys or maybe various ceramic systems or even polymeric systems also. Okay, so that's something which is very fundamental, which you need to know is at the fundamental level. That's the purpose of these lectures. And when you complicate phase diagrams like this one, which is a eutectic phase diagram, you see there is a eutectic point here, right? It's between silver and copper. You know, silver copper eutectic is very important material for various purposes. Think of solders, okay, little bit higher temperatures obviously. Think of, you know, conductive materials, both are highly electrically conducting materials, or if you want to create different kinds of morphologies in nano scale, this is one of the ideal system to study and understand it, okay. So that's severely affected by the size. You can clearly see bulk one is sort of dotted blue, and then 10 and 2 nanometer size particles are showing red and green respectively. So you could see that these effects are very, very significant. They are not small effects. So that's why we need to know how these effects can be understood, or how these effects can be easily tabulated using the mathematical formalisms, using thermodynamics actually, because thermodynamics dictates the equilibrium of phases. Okay, that's the thing which will be taught to you again and again for various subjects. Well, not only that, I also discussed, maybe we'll come back 1 or 2 lectures later, it is not in the size, but the shape of the particles also change the phase diagrams. You can clearly see this is for copper and nickel. It's plotted in the other way, okay. Nickel on the left side, copper on the right side. Nickel is high melting temperature. That's why it is looking lens, but other type of lens, okay. Other type of lens means the orientation of the lens is different, okay. So now the question is this, depending on the particle is dodecahedron. Dodecahedron means there are 10 faces on the solid, icosahedron 13 faces solid, cube 6 faces solid, sphere, octahedron or tetrahedron. There is a significant difference as far as the how the phase diagram look, okay. So size effects is complemented by the shape. So you know that if shape is a very important aspect, because that also dictates the area of the nanoparticles. Even that also dictates changes the curvature, okay, depending on which facets are available on that particular shape. So that means that you need to know both the effect of size and shape. So we are only discussing about the effect of size right now. Well, you know, that's so most of you will be dealing with free nanoparticles, like chemically synthesized, or maybe you know, thin film deposited in a substrate. But many of you will be dealing with bulk nanomaterials. Like let us think of a copper, a rod of copper, a rod basically, okay, like this kind of rod. You see that this is a pen, but this is the shape of a rod. But it consists of nanocrystalline grains of copper. That's what is shown here in this picture on the left side, nanocrystalline grains of copper. Now these grains are separated from each other by boundary. That's what we call it grain boundary. Okay, every grain will be separated by the nearby grain by a boundary. Now, have you ever thought the structural difference, atomic structural difference between the grain and the grain boundaries? That is a distinct difference, okay. The grains will have well arrangement of atoms, on the boundary will have a haphazard or kind of a random or semi-random kind of arrangement of atoms, right. It is not order at the boundaries. So that is what is the truth. Then grain boundaries by default or by de facto, because of its atomic structure, are going to have a higher energy compared to the grains, because atoms are nicely arranged, but in the grains gain boundary it is not. So, this will lead to extra energy. So, this boundaries are called as act as interface boundary. Okay. So, they are not surface, but they are actually interface, and these interfaces will have high energy. In a nanocrystalline size of grain, this boundary area is pretty large, and as you know, total energy of the system is gamma multiplied by A. So, therefore, this is the gamma is one aspect, area is another aspect. As we increase area, total energy, surface energy will increase, and this will have a serious consequence on the stability of these grains, and that is dictated by what? Thermodynamics. Okay, stability is dictated by thermodynamics, whether these grains will be retained in the size or not, or they will coercion over the time scale, that all will be dictated by the thermodynamical aspects or stability aspects of that. So, this is what I have shown you. The gain boundary structures is completely different from the grains. In the grains you have a well arrangement of atoms, gain boundaries will have different atoms. Okay. Well, so that is something which has been discussed from the days of Hubert Gleiter long back 1980s to now, and people have really converged this kind of structures are possible in the nanocrystalline materials. Okay, now as you know, we are talking about effect of size on the phase diagrams. So, what did I do? Okay, so very simple thing we did is that total free energy system has two parts. One is the bulk. You know, I am writing all as G because we talk in metallurgy or material science, we use all as Gibbs free energy. Gibbs free energy is predominantly used. Physics community use Helmholtz free energy. Okay, that is a different thing. Not so much different, but there is distinct difference between these two. But we are talking about Gibbs free energy, so let us focus on that. So, G total, Gibbs free energy total of a system is G bulk and G surface or interface, right. In a nanocrystalline bulk material, you have gain boundaries, that is nothing but an interface. And what did I do? I did like this. The bulk has three parts. This is known to most of you. It is the physical mixture, that Xa Ga 0 plus Xp Gb 0, and because of atomic mixing which leading to solid solution formations, what do you have? You have a entropic change that is dictated by this term XRT Xa ln A plus Xb ln B. Remember, this ln terms are log terms. Okay, this directly comes from you know, Boltzmann's law. You can do that, and along with that you have to add an extra term that is known as excess. Many people write excess. Okay, and obviously because it is bulk, we have to write this. Correct. Now, what is this term? This term we have already discussed, right? Because you are mixing them together, the bond characteristics are changing. Depending on the characteristics of the bonds, you are going to have extra term like this. Remember, okay, I should write x properly, they are not different x, remember. This term omega is basically equal to coordination number multiplied by Avogadro number by 2 EAB minus EAA plus EBB by 2. I do this thing repeatedly so that whenever you are starting a lecture, it gets back to you. You don't misunderstand me, don't try to misunderstand me. These are intentionally done so that you can have a better feeling of the things. As the equations do appear again and again, you will have a feeling what is the meaning of physical meaning of these equations. Okay. Now, this is G bulk, right? Obviously, you need to write this one also bulk. Okay, better to write. Then G surface or interface is written very simply for a spherical particle. You know that twice gamma is surface energy, V atomic volume by radius r multiplied by c, where c is a constant, depends on the shape. Okay. Now, other than that, you need also the molar volume of the whole thing. That is nothing but Xa, Vma, Xp, Vmb. Okay. Let us write it properly. There is a systematic way of writing things. Because that is you need in the G interface term. This term will go there. Okay? Okay. I understand. Correct. That is what you need. The V atomic volume will go. Because it's a molar, that's why we are writing M. Correct? So, how do you get it? For B, pure A and pure B, you can easily get it. You know the molecular weight and you know the density. Then divide molecular weight by density, you get molar volume. That is easy. Then you know the mole fractions X and Xp, you can do a simple maths to do that. But you know also, we pointed out gamma, which is the interfacial energy or the surface energy, it is also for an alloy a strong function of Xa and Xp. But in normal calculations, if you want to use this methodology, which is called Calford methodology, very simple one, you ignore that. You do not consider gamma to be a function of Xa and Xp, because that will make the equations non-linear and difficult to solve, but it is possible to solve. Okay. So, now you know these aspects. The question is, how do I build in the gamma as a function of composition? That was something which we started up and we discussed. So, you know G, I did something, I will repeat it, is this, and dG is known as a V dP minus S dt, right. This distribution we have done. So, therefore, you know for pure dG bulk, for pure, this is pure, suppose pure means without any change of chemical, you know, other entities actually. It is pure A, pure B. So, this is equal to B bulk dP minus S bulk, and B, you know, volume, and S is the entropy, right. But for an alloy, when you have 2 components or 3 components, what do you have? When you have an alloy, you have an additional term. dG bulk is B bulk dP minus S bulk dt plus the chemical potential terms mu I dNi bulk I going to 1 to n. Yes, you can have solution consisting of n number of components. Okay, it does not matter whether it's n is 1 or n is 2, it can be generalized. Okay. So, now correct, but what about same thing for alloy at the nanocrystalline size? Nanocrystalline size means very small size. What will happen? You have to add some extra term. So, that is why we write dG nano is equal to P nano. Okay. dP S nano dt plus I equal to 1 to n mu I nano dNi nano. That is for the bulk. Then you need to add surface energy term or interfacial energy term, that is gamma and dA. Correct? size multiplied by that. Okay, but gamma is independent of anything, we always assume. That is why it is gamma dA, otherwise it should have been gamma dA plus A d gamma, but because gamma is, we are assuming to be constant in all the calculations so far, we can ignore d gamma term. Okay. And if you have, if you are considering the bulk nanomaterials, so you have a gain boundary structure, gain boundaries, then this will be GB I have to be careful when writing. Plus gamma gain boundary GB gain dA gain boundary, right? That is understandable. Many times people, so this gamma is different here for the equation. This is suppose, let us suppose this is 1 for bulk, this is 2 for alloy, 3 for nano alloy, and 4 for nanocrystalline material bulk, wherever gain boundaries. Correct? Correct? You understand that? Now we will take up the last equation. Go to the next slide. So I have to write it out. You don't have to write. So if you write out the last equation, so that it becomes helpful. That's the job of a teacher. Write as many times as possible so that it becomes understandable for the student. Right. So this is GTA, GB is superscript. GB is always a superscript because it's talking about gain boundaries. Right. Now, when you do this, when you have such a kind of structures, when you have gain boundaries and grains, just now I shown you. So two other conditions to be made also. This is a system, right? Gain and gain boundaries. Obviously, the first condition to be met is mu I GB must be equal to mu I grain, or rather bulk. Inside the grain, its atoms are in like a bulk state, all the bonds are satisfied, only the boundaries they are not, right? Because haphazard arrangements of atoms are present, just like we have discussed in case of surface. So the interfaces are also similar types. They are dangling bonds or wrong bonds, all kinds of things are possible. Because of that, you have energy increase, correct? But this condition, which is the gives conditions that interfacial energy across the interface, grain and gain boundary must be same. Otherwise, thermodynamic stability will not be valid. This is very fundamental. You can derive it. In fact, this is what you can find in many of lectures myself on phase diagrams or maybe thermodynamics of materials or phase transformation of materials. This equation is derived. These conditions of equality of chemical potentials of any component in both the phases must be equal at equilibrium. And secondly, you need also to follow this condition also. For any component I, this bulk must be equal and negative for that component to gain boundaries. What does it mean? That means if you have a transport of mass from the grain to gain boundaries, opposite is true, loss of mass to the gain and gain of the mass to the gain boundaries. So this total mass should be conserved. So dNi bulk plus dNi gain boundary must be equal to 0. There is no gain, no loss. If you transfer from one place to other, the place from where you are transferring, that place loses, and the place where it is getting transferred, that place gains. So if it is transferred from gain to gain boundary, that is what happens. It can also happen from gain bound to gain, correct? If a gain boundary is consumed, then this will not happen. If the gain boundaries are created, then other things will happen. Nonetheless, this vital conditions to be mass transport condition to be satisfied. So now, as you know, if you consider only for a bulk material, thus we have written Okay, these are all 3, 4, 5 equations. Okay, so now I go back here. Okay, I erase this part. That's what I did. I'll go back there, erase some part of it. Oops, why did I do it? Okay, let us write it down. So I'm just size effects I'm erasing now. We'll go back to bulk and then start deriving some equations so that you understand. You know, our basic purpose is to calculate the gamma as a function of chemical composition. That is what is our basic job. In order to do that, I am explaining many fundamental concepts so that you don't forget it and nothing, you know, is lost. Correct. So what was this equation for alloy, which I mistakenly removed? dg bulk, v bulk, dp minus s bulk dt bulk, right. So at constant pressure and temperature, what is the meaning of that? dp is 0, dt is 0, because temperature and pressure are constant. So therefore differential of those two are 0. So dg bulk become only dependent on composition. Correct. So if I integrate that, I get g bulk nothing but let us write down. So this was I write down 2, this is 3, this is 4, right. So if you differentiate now totally, okay, this term, what do you get? dg bulk, total differentiation, okay. Mu I bulk dni bulk plus ni bulk d mu I bulk, correct. So this equation I term as 5. Now if we compare equation 3 and equation 5, these two, if we compare equation 3 and 5, okay, these two equations especially, what do you get? Compare means you suppose subtract. You will simply you will get this. Correct. Ni bulk, summation over Ni bulk, d mu I bulk 0. This one, this is known as Gibbs-Duhem equation for bulk. Many of you have studied that. It's nothing about it, okay. So now because I am doing this calculation again, I erase some part of it at the top and bring there, because we can finish it up in one slide so that you can understand. So that means this is for the bulk, okay, everything is bulk, you see. So what will happen to nanoscale? Same thing analogically, you can write down same thing for nano. What will happen is this I1 to n, ni nano, d mu I nano plus gamma Ta. No, that is not correct. Why? Because gamma dA will get cancelled. What will happen is A d gamma. This will all become a 0. So, that is the difference between of Gibbs theorem equation for the bulk, and this is also Gibbs theorem bulk and nano. So, nano you are adding a term A d gamma, correct. So, that is the difference between bulk and nano, right. So, now let us go forward and with this equation, correct, we will apply some constraint or constraints rather, which I have already discussed for this equation, and try to derive the gamma as a function of composition, right. That is what we will do. That is why you have a d gamma term, right. So, those who are smart guys, smart girls, they will understand why you have a d gamma term there, because we would like to know gamma as a function of composition. Then our job is done. Then you can plug in that equation into the model which you have done. Okay, if you do that, you can plug in there this gamma and do the calculation, right. So, okay, you must be looking at this gamma, right. This G interface term gamma is there. So, gamma we can plug in there as a function of composition, make the equation much more reliable. Okay. Okay. So, as you know, mu I bulk is equal to mu I nano. Okay, or let us simply change to gain and gain boundaries. That becomes very easy, right. That is much easier. So, I am putting this also gain boundary. Okay. Why I am doing that? You must be thinking, why sir is doing this? Because the analysis will be same, but because we are discussing about gain and gain boundaries, this will be making our life much easier for you to understand. That is the only purpose. You can always write down nano and keep on doing the calculation. Am I right? So, this gives us d mu I bulk is equal to d mu I gain boundary. You can always differentiate, correct. So, then I can use this equation, which is maybe 5, into the top equation, or 4, you can do that. Okay, you can put this equation there. So, what will happen? Well, this means Ni G mu I, there is additional step which I am missing, d gamma is equal to 0, right. This also can be written as less. You are thinking why I am doing that. Because this is also equal to 0. This is the Gibbs theorem equation, Gibbs theorem equation for the bulk. Summation over Ni bulk d mu I bulk is equal to 0. So, 0 0 you can always equate, right. There is nothing wrong about it. This term is also 0, this term is also 0. So, you can always equate these two terms. Mathematically, this is nothing wrong about it. Okay. Physically, there may be some problem. Mathematically, we can do this. So, now, because we have done this, the top equation, now we can always write down d mu I G B A bulk d mu I G B. This term, because of this equality, I can change over. So, finally, what do you get? Finally, if you do a math carefully, you will get d gamma is equal to minus I equal to 1 to n d mu I g b n I g b minus n I bulk by a g b, correct. So, you could see that finally, after doing so much of maths, you must be thinking I could relate d gamma as a function of composition and the change of chemical potential of the gain boundary. Now, my task will be to convert this change of chemical potential into composition, then I am done actually. Then I can relate, integrate this equation and get gamma as a function of composition. How do we do that, right? Well, that is not very difficult to do. Okay. Why? Well, first of all, this is always written as summation this term divided by AB GB is written as a sigma I or gamma I, sorry, capital gamma I, right? You understand that. So, for binary system, binary means AB d gamma is very easy, right. This is what we can write. So, we will use this one from now onwards, because binary is easy, forget about summation size, you can use the binary. So, now in order to convert this, this, why do we use this kind of capital gamma? Because of isothermal effects, okay, that is why, adsorption effects. So, whenever you have a nanocrystalline gain, composition of gain boundaries will be different because of the chemical potential equality and many other transport effects, correct. So, now I am going to erase this part which we kept it. So, here as you have seen, d gamma has become a very simple equation for binary, that is minus, okay. This is what is d gamma is. Now, to oversimplify it, that is what we will do. We can apply Henry's law. Why? What is Henry's law, by the way? Henry's law, many of you may not know it. Let me explain it and we will come back. We will apply Henry's law to this. Okay. Let me just discuss. What is general form of chemical potential? General form of chemical potential is mu A equal to mu A 0 plus RT ln, okay, activity A. And activity for gas, it is written as a PA, suppose PA by PA 0. In a gas mixture, partial pressure of A divided by the pressure of pure A. That is what it is. Okay. So, if it is 1 atmospheric pressure in the air, partial pressure of oxygen is 0.2, 20% oxygen. So, 0.2 is divided by 1, that is what the activity of oxygen in the air. You understand that? So, in a gas mixture, if you have two gases, hydrogen and helium, 40-60. So, if you want to calculate the activity of hydrogen, that is 40, but 0.4 divided by the total pressure, that is equal to 1 atmosphere. Okay. So, that means 0.4, right. That is what it is. So, now Raoult says, well, to understand the solvent and solute effects in solute solutions, Raoult came into picture and he says, why to use such a kind of complex things? He said Raoult mu A is equal to mu A 0 plus RT ln XA. Simply you arrived on the mole fractions. That means, according to Raoult, A is equal to XA, mole fraction. Okay. That is what it is. Quantity A is activity. Now, well, so that is what it is. So, but to generalize these things, one can say A is equal to gamma A into XA. Well, we should not write gamma A, it will confuse. Let us write down something else. So, write down epsilon A into X A. So, epsilon A is constant 1, that is for Raoultian, and it is not equal to 1 for others, correct. It can be less than 1 actually most of the cases. For Raoultian, for the Raoult's law, this will be equal to 1, then its activity become mole fraction. But you know, Henry says very dilute solutions, okay, only in the ends of the phase diagrams where solutions are very dilute, like 2%, 3%, 5% concentration of the solute. Henry says mu A is equal to, or basically Henry says much easier way, Henry says partial pressure, I can use partial pressure equal to K constant multiplied by XP. Kb is a constant, that is what is not Krishnavishwas, that is Henry's constant, okay. You should remember that Pa is equal to Kb into Xa. So, if you put back that, so mu A, sorry, no height is B, it should not be B, right, it should be A. Okay, B is solute, that is why A is a solvent. Dilute solutions. So, A is applied, A is solvent basically. Raoult's law is mostly applied for solvents, and Henry's law is applied for dilute solutes. Okay, solute solution, but solute is dilute. Dilute means very small concentrations. So, mu B may be 0 plus RT, okay, ln Kb by Xp can be written as mu b 0 RT ln Kb, sorry, Kb Xp, right? Why I am writing Kb by Xp? That's mistake. You should point it out, right? You are not here, that's why you are not able to point it out. So, these can be added together because Kb is a constant, that is a Raoult's, sorry, Henry's constant. So, that is why it can be written mu 0 star, right. So, what is d mu b? This is a constant, so this becomes 0 RT dxb by xp, got it. So, this is what it is. So, now I go back here, plug in that. So, d gamma is mu A into RT divided by XA divided by XA, correct. Bulk multiplied by dxa bulk, right. Am I clear? Remember, we are not using surface energies here, that is why. So, I can write down d gamma by dxa bulk equal to minus this term gamma A RT by XA bulk, right. Well, since we have to bring in the effect of gain boundaries, what do you do? Very simple. Okay, we are almost done actually. So, we can always assume this gamma, if this absorption thing, which that is why the nano effects are there. Okay, you remember that, you know why? You see, this AGB is there, mu GB, all GBs are there, gain boundary terms are there in this term. This is equal to this, right? So, this can be simplified to make life very, not very complicated. This can be simplified. Okay, where delta is the thickness and rho is the density of gain boundaries. These are very difficult terms. So, thickness of gain boundaries can be obtained, density of gain boundaries, well, it will be less than the grains because it has more random grain atomic structures, but one can actually measure by looking at the gain boundary structure very easily. You know the gain boundary volume, then you can know the number of atoms present, then mass by volume can be obtained as a density. So, if you plug in there, so d gamma become what? Minus XA GB by XA bulk, correct, RT delta rho d A bulk, correct. So, that is why gamma can be written as gamma 0 minus RT, okay, del rho XA GB log of XA bulk, that is it. So, if you can get an expression like this after doing so much of mathematical calculation in the last half an hour or so, then you can use this expression and put it here in this gamma term. So, as you see here, because it is a function of x a, virtually it is a function of x b, x b and x c are related, x a plus x b equal to 1. So, that means this is a non-linear functions now, gamma, and that is what something which you should remember. So, by doing this, you can simplistically, you can actually put a relationship between gamma and compositions and do it. And for nanostructured materials, it is rapid, it is widely done. It is widely done, nanostructured materials, okay. Remember this, it is very easily done. Now, before I wind up this lecture, let me tell you, this is a very simplistic thing, one can even use little more rigorous analysis and derive this equation. These are known as a Butler's equation, which you know actually, there is nothing in knowing, but this will not be part of your exam, Butler's equation, where this gamma is related as a gamma, pure gamma A divided by, this is a little bit complex and difficult to derive, G excess surface minus A excess bulk, you know G excess bulk, gamma x x b, right. In the G excess surface also can be obtained if you know the surface composition, RT by AA 1 minus XA surface 1 minus XA bulk, okay. And then what is A? A is interfacial area, right, and these excess terms, surface and bulk, their partial molar free energy, of surface or bulk. Yeah, for bulk you understand, no? For G excess bulk I have written already gamma XA XB. So, these are all bulk composition. So, G excess surface will be gamma XA surface XB surface. So, one can use this also, straightforward. So, either of these two equations, but this one is very simple, okay, which you have done that, and you can plug in there. So, that is something which you should know, that is why. So, then if you do if you put these things into a model and do a better computational work, you can easily get effect of composition on the surface energies, and this is very important for many of these alloys. Without doing that, you will be doing a huge mistake. The accuracy of your calculations will be pretty low. So, that is why one has to know this mathematical formalisms and plug in these equations, and that is the purpose what I took so much of time to derive that, correct. That is the main reason why I spent so much of time to derive this, okay. So, in the next lecture, which is lecture number 14, I will be talking about the generalized equations, okay. I know you are getting quite a bit load it with mathematical things. But that is the last thing which I will do, generalized equations for free energy for nanomaterials, which can be used for anything. You can use one equations to solve mathematically or computationally the phase diagram problems. Okay, so let us stop here. Thank you. We will come back to it the next lecture, that is lecture 14, and discuss about this. Thank you.